Hello class, today we're going to do a short video on logical translation. In this unit, what we're going to learn is how to see and find the logical operations and symbolize them in our everyday sentences. So what I've done here is I've written up our logical symbols. I'll go through all of them and explain how they work and how to look for them in regular everyday sentences. And then over here, I've written up play everyday sentences in order to work through some examples of ways in which the translation from regular grammar to the symbolized grammar of logic will work. Okay, so when we're doing deductive logic, we have here 5 symbols, and these will define all of the possible operations that at least you will see in this class, and largely cover most of the logical language that we use in our everyday life. And the first of these is the tilde, right here, which indicates negation. It is a not statement. And so when we see a sentence that is negated, that has any form of negativity, a double negative, so like it's not the case that I won't go to the park, that's a double negative, right? I might write something like not P. And what I've just done is given you the first example of the way in which we can translate our sentences into a deductive logical form, where I've represented a part of the sentence. I will go to the park as P, and then I've represented the logical language that also appears in the sentence that I gave as separate from, but operating on that sentence. So it's not the case that I will not go to the park, right? So what we're doing in translation is distinguishing between the simple components of a sentence and the logical operators that are in them. And again, that's how negation works. Negation is just a single place operator, so I won't go to the park, symbolized there. That tells us that something won't happen, that it can't be, that our simple sentence is negated. Okay. Our second symbol is conjunction, sometimes written as an ampersand, sometimes written as a caret. In this class, our book uses the dot notation, so that's what we're going to use as well. And I believe the reason it uses the dot notation is because the dot is favored by the computer science departments, but don't quote me on that. In any case, they all mean the same thing, but please, for the sake of this class, use the dot. And as long as we're doing online work, all of these symbols will appear in the problems on your quiz and on your midterm. Just copy paste them from the quiz itself, because it's kind of a pain in the butt to get the Unicode stuff to work. But copy paste is just fine. So anyways, this is conjunction. So let's say I have P equals I will go to the park, right, written here. And then let's make A, Andy likes barbecue chips. Okay, so now I have 2 simple sentences. Now, before I explain what conjunction does, notice that these sentences have a subject, Andy, and a predicate, likes barbecue chips, likewise I being a subject and will go to the park being the predicate. You should only have 1 predicate and 1 subject per simple sentence, and there should be no logical language. So say for instance in our sentence here, Bob and Socrates went swimming, we notice that there's a logical operator here. What we should be doing is separating the subjects from the shared predicate, and we can tell that by looking at the logical operator. So what the conjunction does in this example is it takes two subjects and applies them to one predicate. So what we should be doing when we're translating is just finding what the atomic parts are, the single units of subject-predicate relations are in our sentences. So if I say something like, Andy and I will go to the park, there's two atomic sentences. There's I will go to the park. In addition to that, there's Andy will go to the park. And what I've done is I've conjoined them together by saying Andy and I will go to the park. And this, again, is how conjunction works. So if I have the sentence Andy and I will go to the park, I see that there are these two atomics in it. There's P and there's A. And so I want to notate this in logical symbolism because I don't want to write out that whole sentence. So what I'm going to do is take my two variables, P standing for the first atomic, I will go to the park, A standing for the second atomic, Andy will go to the park, and I can join them, like so, P and A. Okay, so what this just tells me is that there's a conjunction of two atomics, and then I have a key up here that tells me what each of the variable atomics means. So P means I'll go to the park. So I'll go to the park and Andy will go to the park. That's our symbolization for conjunction. Okay? Now, I suppose before moving on, we can compound these. We can add them together. We can use multiple logical operators in one sentence. So how about it's not the case that Andy and I will go to the park, because right now it's raining and nobody wants to go to the park in the cold rain in the evening, right? So anyways, it's not the case that Andy and I will go to the park. So what we should notice is, well, Andy and I will go to the park was represented as P conjunction or dot A, P and A. But there is another piece of logical operation going on there, which is the not. It's not the case there. And so what I'm going to do to represent this is I'm going to put parentheses around my P and A, and then I'm going to draw a tilde. So this tells me that it's not the case that these two statements in conjunction are true. What the parentheses do is they separate out the atomics from the negation. So what we see here is that there's a main operator. It's the operator that has the widest scope. So say I have P, Q, not the case, or it's not the case that Q and P. Okay, so in this sentence, and we'll get to what all this means, but the main connective of this sentence is the connective with the widest scope. And if you can see, it's not the case that if P then Q, or it's not the case that if Q then P, which it turns out that this is self-contradiction, but we'll get to that in the next video. The operator with the largest scope is the V here in the middle. It's not the first operator because this negation, this tilde, only operates on this if P then Q. Likewise, this tilde only operates on this if P then Q. And these horseshoes only have two variables. But the variable, the symbol with the largest scope is our main connective. It's the one in the middle that connects up the whole thing. Now, in this case, our main connective is the tilde because this dot only operates on these two, the P and the A, whereas the tilde operates on everything altogether. So our tilde is our main connective in this case, and it tells us that it's not the case that Andy and I will go to the park. So notice what I do here. I'm going to erase these parentheses, and I'm going to say, okay, well, it's not the case that Andy and I go to the park. So it's not the case. I know that means tilde. Andy will go to the park, and I will go to the park, right? But I've done something wrong. What I've written here is it's not the case that I will go to the park, and it's the case that Andy will go to the park. So by removing the parentheses, the scope of the tilde here is reduced to just the first letter, just the first P. So this is telling me that Andy's going to the park, but I'm not going to the park. And that's not what the sentence was. The sentence was, it's not the case that both Andy and I will go to the park. So it's really important that you put parentheses around all of your individual variables as they are dedicated to the certain operations of a sentence. And if you don't, then what you write or what you symbolize could mean something very different. So be careful about that on your quizzes, and notice how they work in the examples in the book. But that's one thing to be on the lookout for. It's an easy mistake to make. It's also an easy mistake to avoid making. Okay, so we've done negation, we've done conjunction. How about disjunction? And you should notice that out to the side, these are the formal names: negation, conjunction, disjunction, equivalence, and implication. I've also written the informal names and how they sort of appear in everyday sentences. Disjunction is our or. It's an either or. It's an unless, but, neither nor, that sort of thing. So either I will go to the park, or Andy likes barbecue chips is going to be P or A, which tells me that it's either the case that I go to the park or Andy likes barbecue chips. Okay? That one is pretty straightforward. When we get to truth tables with this stuff, we'll notice that, I'll save that for when we get to truth tables. Okay, so that's disjunction, our V. Now we have implication. So implication is symbolized as the horseshoe here. Sometimes it's also symbolized as an arrow. Again, in this book, they use the horseshoe notation, so that's the one we're going to stick with. It's important to be consistent with your symbolization because symbols can mean different things in different systems. We're using the horseshoe, so stick with that one. Again, copy and paste it from your quizzes online. So implication is a conditional or in more colloquial language, an if-then statement. So if it's the case that I go to the park, then Andy likes barbecue chips. So what I've done is I've set up a conditional statement. I've said that conditionally A will be true just so long as P is true, right? That if it's the case that P, then it's the case that A. Now I can do this the other way around. If Andy likes barbecue chips, then I will go to the park. So what the if-then statement does is it sets up a conditional or an implication, the implication being of P from the condition A. Now, we should know one thing about our conditionals and our implications, is that there's a really particular name for this right here and this right here. The thing that the letter that occurs on the left side of our horseshoe and on the right side of our horseshoe. And the names for these are necessary and sufficient conditions. So when I say, looking at if A then P, what's the necessary condition? The necessary condition is whatever occurs on the right side of the horseshoe, sometimes also called the consequent, because if this is an implication, the consequent is what is the consequence of whatever condition we've set up that will imply it on the left side of the conditional. That one is often called the antecedent because it's what comes first. It's anterior, comes before, and it's also a sufficient condition. And so what do these mean? Well, A being sufficient for P means that anytime there's A, then P will also be true. That A is sufficient for P, that A is, it contains in its truth as well the truth of P, just given the truth of this conditional. Now, likewise, being a necessary condition means that you can't have A without P, that P is necessary. So that's sort of what we're saying. We're using these words to indicate the two halves of the implication going one way and the other, where necessity says that P is necessary for A, and sufficiency says that A contains the truth of P, just given that conditional is true. Okay, so that's our implication, or our conditional. The last of our logical symbols is equivalence, which is an if and only if. Again, sometimes it's symbolized as the double arrow here. Now, the reason it's symbolized as a double arrow, because the first implication was an arrow, this is why we get equivalence, because the implication goes in both directions. So if I have, and again, that's this triple bar here, we're using the triple bar notation. If I have P triple bar A, I read this as P if and only if A. So what this tells me is that I will go to the park if and only if Andy likes barbecue chips. And there's a certain way that we break this down. This sentence is logically equivalent to if P, then A, and if A, then P. So what the equivalence statement says is that this statement is the same as the double implication, the implication going in both directions. That you don't get the one without the other, and you don't get the other without the first. So they both require each other, that they're necessary and sufficient for one another, or otherwise equivalent. Okay, so that is our set of symbols. Now let's go through some examples, and I put in some tricky ones here. I think I tried to keep it easy when I was writing the quiz on tricky questions. I think there's one only if question on there, but you'll have to see. I wrote these up to reflect similar language that's in the quiz. Okay, so Rolex does not make computers. How are we going to symbolize this? Well, the first thing that we should do is we should be looking for the logical operator, and we should be looking, or operators if there's multiple, and we should also be looking for the atomic statement. So right away, I see that there's a not here, so I'm going to circle it, and I see all of a sudden that there's Rolex does something, so there's a subject, and then whatever Rolex the subject does is going to be our predicate. So I'm going to underline this, and all of a sudden I have my atomic sentence. So my atomic sentence is Rolex makes computers, but that's false according to this sentence. The sentence tells us that Rolex does not make computers. So if Rolex makes computers is written as R not is going to tell us that R is false. It's false that Rolex makes computers, and that's how we symbolize that statement. Okay? Socrates didn't eat Jell-O. Now, this one's maybe a little tricky because there's no obvious not, but the didn't is a negative statement. That if we broke down the syntax of didn't, we would get did not, right? So my atomic statement is Socrates did eat Jell-O, right? Because any atomic statement is not going to have any logical operators. That's really important. We're separating all of the logical operators away from our atomic statements. So Socrates ate Jell-O. We're going to symbolize as S, and then our didn't, we're going to give it tilde. Okay, Tina ate Jell-O, but Socrates ate bread. Here's a tricky one, and I don't remember if I wrote one in the quiz like this, but it could come up. But is our logical operator here. And the reason this is tricky is that but often sounds, at least it did to me when I was first learning this stuff, but often sounds a lot like or. That, well, this, but maybe also that. But it's not the case that but indicates or. But is another word for our conjunction. So I'll write that here. And. So when you see but in a sentence, you should be thinking conjunction. Now, this one's also tricky because it contains two atomic sentences that share one predicate. So our predicate is ate bread, but we have two subjects. We have Socrates and we have Tina. Oh, sorry. We have two predicates and two subjects in this one. So ate Jello is one predicate, ate bread is one predicate, and we have Tina and we have Socrates. We have two atomic statements being conjoined with a but. So I'm going to represent Tina ate Jello as T, and I'm going to represent Socrates ate bread as S, and then I'm going to represent my logical operator, my conjunction with the dot, T and S. Tina ate Jello and Socrates ate bread. Good. Okay. This one. Bob and Socrates went swimming. This is where there's two subjects. There's Bob and there's Socrates, and they share a predicate. Now this is okay. You can share a predicate. We talk in this way all the time. But it's important to separate the two atomic statements because every atomic statement, again, is a subject and a predicate, and there can't be more than one subject, and there can't be any logical operators in it. So breaking this down, we see that there are two sentences within it, which is that Bob went swimming, and there's also Socrates went swimming. So I'm going to represent Bob went swimming as B. Now I should notice the logical operator and, so I'll represent that here. And then our second atomic statement is that Socrates went swimming, which I'll symbolize with an S. Good. Okay, on to disjunction. Either Jimmy snowboards or he skis. So this one again is a little bit weird because we have one subject and two predicates. Jimmy snowboards, Jimmy skis. It's also a little weird with how you choose variables to represent things. It honestly doesn't matter what variables you choose, again, just so long as you're consistent. So I could have represented Bob went swimming as X and Socrates went swimming as Y, just so long as I state what it is that I'm interpreting my sentences as being representative of in variable form, then I'm okay. So this one is a little funky because snowboard and ski both start with S and Jimmy is J. So I might do something like an X and Y here so that I can keep myself straight. So I might say Jimmy snowboards is X and Jimmy skis is Y. And what I see here is either or is my logical operator. So it's either the case that, I think it was just off screen, sorry. Either it's the case that Jimmy is going to snowboard or he's going to ski. So I'm going to represent that with my V. Good, okay. So Tiffany likes the rain or snow. Again, we have one subject and two predicates, likes the rain or the snow. So let's say Tiffany likes the rain is T and Tiffany likes the snow is S. Again, I'm going to put a V in between those, and I've represented this sentence. Okay, now finally on to implication. If it rains, then the ground becomes wet. So I'm going to circle my logical operators, my if-then, and I know that whatever comes after an if goes on the left side, right? So if it rains, I'm going to represent as R. This is our antecedent or our sufficient condition. Then, and whatever comes after then is going to be our necessary condition or consequent. If it rains, then the ground becomes wet. So if R, then G. And following this rule, whatever comes after if and whatever comes after then as being the necessary and sufficient condition, or the antecedent and the consequent, is generally a good rule to follow, with one exception. And I wrote this exception here, and I believe this one does show up on your quiz. Be careful about it. It's the only if. So the ground becomes wet only if it rains. You'll notice there's no then, which should key you on to something weird in this sentence, but there is an if. And when there's an if, we know that we're talking about implication. The ground becomes wet only if it rains. This is the phrasing that breaks the rule. Because what only if does, when if indicates what the antecedent, only if indicates a consequent. When we say only if, we mean that it's a necessary condition. This would be represented as if G, then R. And here's why. The ground becomes wet only if it rains. So if the ground becomes wet, then it rains. And what this means is that the only if being a necessary condition will go on the right side, because what our sentence is saying is that the rain is the only possible scenario in which the ground becomes wet. So if the ground becomes wet, then it must have rained. And it's kind of a weird, circuitous way of thinking about implication, but it is a really common one. We say only if things all the time. And so it's a tricky statement, but it's one to be aware of, and it's one that you should keep in mind. Now, here's something that might help understand the only if and the difference from an if then just generally. Besides just sort of like brute force memorizing this, right? Only if means necessary condition. What you can do is you can think of our equivalent statement, or triple bar, which is the if and only if. So an if, or an if then, in an if then, an if indicates sufficient condition. But in an only if, it indicates a necessary condition. But what we recall, or should recall, from our equivalent statement is that you only get the P if you get Q, and you only get Q if you get P. It's both, right? It's P, then Q, and Q, then P. So I have both forms of the implication equivalent to P if and only if Q. So this if and only if is equal to this. The if and only if is supposed to indicate that P is both a necessary condition for Q or a sufficient condition for Q, and it's a necessary condition. And likewise for Q. Q is a necessary condition for P, and it's a sufficient condition for P. It's an if and only if. So here we get if and only if. So if I were to say, IFF means if and only if. If and only if if and only if the ground is wet, then it rains, which is just G R. And this language, the if and only if, it's pretty unique, and almost even unique to deductive logic and philosophy sort of generally, but it's really highly conspicuous, so you should be able to pick it out as unique for what it's doing. Okay, great. So that's our symbolization. Here's our symbols here and all of our examples. Hopefully that was helpful. If you have any questions, of course, always email me. And don't forget to set up your extra credit meeting in person. That's open all semester. Great.